Okay, let's welcome to Calculus, Chapter 5.4, number 20. And boy, they raised the bar for us here. So let's get started with this diagram, critical. Quickest route. Jane is 2 miles offshore. I've got Jane 2 miles offshore in a boat and wishes to reach a coastal village 6 miles down a straight shoreline. 6 miles down, here's our coastal village. From a point nearest the boat. She can row at 2 miles per hour. So I'm just theoretically saying that we're going to go this route. Maybe our best bet is this route, or maybe our best is a straight line. But because we can row 2 miles per hour, we can walk at 5 miles per hour. What's the quickest, the least amount of time? Where should we land the boat? So we're either going to say land the boat X north of the village or X down from where we're at right now. I'm going to call this X. Now, I'm using blue ink for my miles and red ink for my race. There's definitely something that we're going to have to be talking about. So let's get going on this. We may have our calculator help us out with this one a little bit as well. Okay, so if we're coming down this way, if I call this X, then clearly this part is 6 minus X miles. If I call this was 2, and if I call this X, then this distance that Jane would row would be by Pythagorean X squared plus 4's root. So if we were just talking about distances, our distance in terms of X would be square root of X squared plus 4 plus 6 minus X. But we're really interested in time. And our time in terms of X, a little bit trickier, but let's think about this. Let's say Jane actually rows 4 miles downstream. That would be represented by this. And at 2 miles per hour, how long would that take us? Well, we'd take this and we'd divide by 2. So time, this would be square root of X squared plus 4 divided by 2. And likewise, let's say, forget about this 6. Let's say Jane was going to walk 20 miles. We would take 20 and divide it by 5 to see how long we're walking. Or in this case, we would take 6 minus X and divide it by 5. That's the time spent walking. So here's our rowing time and our walking time. Okay, so I'm gonna go ahead and graph this function. We're going to take a look and just see what we're looking for. We're looking for a minimum here, and it would make sense to say that time must be that the value of X, not the time itself, but the value of X. It would make sense that the value of X could be anywhere from 0 up to 6. The value of X, I could stretch this value out right here, 0 to 6. So let's go ahead and make it a little easier for you to see this. Darken that up a little bit and focus. And there's our function. As you can see, you'll notice in my window, I'm 0 to 6. And if I know my domain, I'm going to use zoom fit every time. So zoom 0. And boy, I think we got what we're looking for. And if we interpret this for a moment, this would be X is 0 over here. That means that for Jane to walk straight across, and then, to row straight across and then walk down would take more time than for her to paddle toward her target, but way longer if she paddled the whole route that way. Okay, so there we go. I'm going to go ahead and just copy down this. Even though we're going to go through the calculus, I'm going to get second calc minimum right now. And for the calculus portion, we should really test X is 0 and X is 6 as well. But our graph is telling us that won't be the case. Our graph is telling us that X is going to be approximately 0.873, and we're just going to use that to check a little bit later on. All right, let's get focused here, literally, figuratively. and get going on this. So I know that I'm interested in time at 0. I know that I'm interested in time, what my other choice for x, time for x is 0. I know I'm interested in time for x is the full 6. And I'm probably interested in time somewhere else. Our graph led us to believe that we're interested in that as well. So here we go, first derivative. Careful here, we're going to take our time. If this is to the 1/2, then I would have 1/2 x squared plus 4 to the negative 1/2 times the inside derivative 2x, all on 2, or times 1/2. If I treat this as 6/5 minus 1/5 x, my derivative of this clearly quickly becomes minus 1/5. We just have some cleaning up to do. Okay, so I get 2x times 1/2 is just x in the numerator over 2 times x squared plus 4 to the 1/2 minus 1/5. I'm going to get common denominators. So my least common denominator, I need a factor of 2, I need a factor of 5, so that is 10. I need a factor of x squared plus 4 to the 1/2. I had to multiply this by 5 on 5, and I had to multiply this 1 by 2 times x squared plus 4 to the 1/2. And I'm interested in when 5x minus 2 times x squared plus 4 to the 1/2 equals 0. So we got a little bit of algebra left here to do. I'm interested when the numerator is equal to 0. We don't have any points of non-differentiability, but we do have endpoints, 0 and 6. All right, so let's go ahead and do this. I'm going to go 5x equals 2 times square root x squared plus 4. I'm going to square both sides. 25x squared equals 4 times x squared plus 4. I get 25x squared equals 4x squared plus 16. I get 21x squared equals 16, and I get x, because x has to be positive, equals 16 on 21's root, or 4 on root 21. Could we have it? Let's take a look. On second twit, 4 divided by second square root 21, please, 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 0.873. There we go. That's encouraging. Okay, so at 0.873, 4 root 21, that's our choice exactly rounded. So this would be time. Does it ask for our total time? Let's see. Go back to take a look at this. Where should she land her boat to reach village in the least amount of time? Well, it's either going to be at 4 on route 21 downstream, or 0. If I put in 0, what's our time here? Our time would be square root of 4, 2 on 2. That would be 1. Plus, if I put in 2 here, I get 4/5. I get 1 4/5 hours, or 1.8. If I put in 20 here for my time, well, that stinks. I'm going to go ahead and do this, though. I get square root of why did I want 20? 20 is silly. I have no idea why I wanted that. I wanted t on 4 root 21. If I put in 6, I get square root of 36 and 4, 40, divided by 2, plus 6 minus 6, 0 on 5. and we get 3.162. And then if I put in 6, or excuse me, that was 3.162, darn it. And then if I put in 4 on root 21, 4 on root 21, we can go through the same process again. I'm going to cheat on this one just in the interest of time, and I'm going to go back to y equals my graph, and let's go back to that second calc. Minimum, we knew it was a minimum again. I'm just taking the time right now when I would normally take 4 root 21 and put it in for x and do a calculation there. So right bound enter, left bound enter. 1, try that again. Y equals, I think I did max, second calc minimum. Make sure I get far enough over, maybe that's what I did. And I get 0.8728, and I get 2.116, which makes me wonder about my T0. I get 1 plus, when T is 0, I get 6/5. That's 2.2, excuse me. 2.2, so a little bit of fumbling around there. My apologies there, but when I put in 0, when I put in 0 here, I get 4, 2, that's 2 on 2, 1, plus 6/5, put in 0, 6/5, so that's 2.2, which is a little bit longer for Jane to go straight across 0. So our solution is 4 on root 21, or approximately 0.873 downstream should be her target. Ooh, there's a lot going on in that problem. A lot of thinking, a lot of physics kind of application there, where we're converting distances into time from here to here. Great problem. Here's the news. Would certainly be a problem that could be represented on the AP test, therefore could certainly be a problem that would be represented on your test coming up soon. Hope that was helpful.